Hello, and welcome back to QED and QCD. Let us now try and evaluate the scattering amplitudes, maybe even the cross-section, for a particularly simple example, that of Coulomb scattering, i.e. essentially scattering of an electron of a potential. Now, of course, the potential is generated from a source, so let's look specifically at the Coulomb scattering. Of an electron incoming with momentum p and a muon of momentum k scattering into an electron of momentum p prime and a muon of electron k prime. Now, the Feynman rules say that we need to find all diagrams connecting the two, the initial and the final state, all connected diagrams connecting the initial with the final state. Now, we'll calculate this in perturbation theory, so we will calculate it to a specific order in the electric coupling, in the electric charge E. But let's start by drawing the initial states. Alexa, stop. Sorry. So the electron and the muon then there's a scattering process. They connect into that, and there's an electron and a muon coming out. Like so. Now, we now want to draw all the possible ways of connecting these initial state with the final states. All connected diagrams connecting the initial states and the final state. Since there's no direct interaction between an electron and a muon, we can't just connect the electron and the muon fermion lines. But both the electron and the muon will interact with a photon, so we can connect the electron line and the muon line with a photon exchange. The only way to do that is to have the E of P to E of P prime and the mu of K and the mu of K prime connected with a photon. And we can call the photon momentum Q and count that down. Now, there's no actual significance to the lines being drawn as so with a point. They could be drawn just as a straight line, etc. But let's just draw it like so. This is the only, so there's an electron charge here and there's an electron charge here, so this would be proportional to electron charged squared. This is the only diagram to draw at this order. If we were to draw the diagrams at higher orders, we could, for example, insert a fermion loop in the photon propagator. Then we would get higher order contributions in the coupling. Now, in this course, we'll just consider Born level amplitudes, so tree level. You'll get to calculate loop in another course. But if we consider, for example, instead of electron-muon scattering, the electron-electron scattering, so E of P, E of K, going to E of P prime, E of K prime, or the positron equivalents, or even the positron E plus or minus, 2 plus or minus, then there will be two diagrams with two vertices at this order. So for example, if we had the E minus, to E minus, E minus, then one would have the same diagrams like so. And those. This is not an interaction here, but like so. No interaction, just crossing fermion legs. Remember, crossing fermion legs is accompanied by a relative sign between these two amplitudes. Good. But let's now stay with this process. Sorry, not this process. Let's not stay with the process of E mu scattering. Good. So what we needed to do with the Feynman diagrams was to use this nice drawing here and convert that to a formula for calculating the scattering amplitude. We also remember that the Feynman rules consist of replacing the drawing here with a mathematical expression, and that this mathematical expression contains vectors and matrices both in Lorentz mu space and in spinor space, and that these quantities, of course, have to arrive in the right order, and that order was to start at the end of a fermion line and work backwards, right? It doesn't matter which fermion line we start with, because they will be connected by a photon propagator, which is just a g mu nu, and the issues with the quantities are mostly with the spinor quantity. So as long as the spinor quantities are arranged correctly according to the fermion line, then you will get the right expression. So let's start with, say, the electron line. So we write Im, that was an M, is equal to the outgoing electron line gives us a U bar P prime. Then for the vertex, we get a I, E, let's call it gamma mu. If this here has a mu and down here has a nu. And then the incoming electron spinor is a U of P. Let's work with this expression a little bit. So in spinor space, this is a covector with 4 entries. Gamma mu, for each mu, is a 4 by 4 matrix. And U of P is a spinor, like so. It's a spinor vector. So in spinor space, this is a number, but there's one such number for each value we take of gamma mu. So in spinor space, it's a number, and in Lorentz space, it's a vector with an index mu. Similarly, let's call this not Im, but just say that the electron line. The muon line will give us similarly a U bar of K prime, a IE gamma nu, and then a U of K. Now for the photon propagator, connecting the vertex with the mu and the vertex with the nu, there's a photon propagator, and that photon propagator will be in Feynman gauge if we have that q, the momentum q is p prime minus p, or k minus k prime, then in the Feynman gauge, where the propagator is particularly simple, the photon propagator is simply minus I g mu nu over q squared. Let's remember the I epsilon, even though for tree diagrams it's not needed. The I epsilon prescription is necessary only for loops, or it has an effect only for loops. Otherwise it's simple to take the epsilon to zero limit. Now, the amplitude scattering amplitude is then, according to the Feynman rules, I m is equal to, we have a I times I, that's minus 1, and then we have a minus I, that is in total an I. Then how many e's do we have? We have an e from here and an e from there, so that's e squared. And then we have the spinor strings. So we have a u bar of p prime, we have a gamma mu, we have a u of p, then we have the g mu nu over q squared, and then we have the muon contribution, mu bar, k prime, gamma nu, u of k. Good. So we remember that this here, for each mu, this is a number because it consists of a spinor covector, a spinor 4x4 matrix, and a spinor vector. The same for this. For each nu, this is a number. That means that in all, this is a Lorentz vector, because there's one such number for each nu, and this is a Lorentz vector here. And those two Lorentz vectors are connected with a g mu nu. So that means that this is a number. It's a vector, a g mu nu, and a vector. That gives us a number. And that's, of course, what it should be. It is an amplitude, and that is just a number. So in principle, if one chose a representation for the spinors, we discussed the Dirac representation, for example, and the representation for the gamma matrices in that, and used the gamma matrices in that representation, then one could indeed, for each choice of momentum, evaluate this number of the scattering amplitude, get a number for the scattering amplitude. And that indeed is what, for example, a tool like MATLAB does. Because just as in quantum mechanics, when we want to calculate the scattering probability, we need the square of the scattering amplitude. But of course, if the amplitude is just a complex number, so it's easy enough to square. To find the mod. If you were happy enough choosing specific representations for the spinors. Now, before people used computers as much as they do now, when people wanted and needed to do pen and paper work, they realized that actually it's possible to write the scattering amplitude squared in terms of invariance, so energy invariance, rather than using spinor representations. It is possible to get rid completely of the spinor representation in the matrix element squared. Let's see how that's done. Often, when one is interested in calculating the scattering amplitude, one isn't actually interested in calculating the scattering amplitude for a given choice of, let's call it, spin, right? Remember that the spinors here depend on the spin up or spin down states. Now, often, I see that it's easier to do it like this. Yes, prime and this. Often one is not really interested in the spin of the incoming particles. What one really is interested in is the spin averaged cross-section, because that one uses spin averaged beams, for example, and one doesn't measure the spin of the outgoing particle, so summing over all possibilities. And that's so frequently the case that one is interested in the spin averaged scattering amplitude that one has a notation for this. And the convention for the notation is to say that one is interested in the spin averaged matrix element, spin averaged square matrix element. Now, that will be equal to each electron can come in two states, and the incoming muon, can come in two states. So if we divide by a half for the electron and a half for the electron and for the muon, and sum over the two possibilities of spin for the incoming particle and sum over the spin for the outgoing particle, whoops, that should be incoming R prime, and sum over the two spin states of the incoming muon, and sum over the states of the outgoing electron and outgoing muon. Then what we have done here is to form the spin averaged sum over all final state particles. Spin averaged incoming, summed over outgoing. So we want the spin averaged cross amplitude, and we construct that explicitly by summing over all possibilities and averaging over the incoming states. Good. Now, what we get there is, of course, that's equal to 1 over 4. And then we pull out the E squared. We get an E squared from M and an E squared from M bar. So, of course, this number here is M and complex M. And from each, we get an E squared, so we get an E to the 4. We get a Q squared from each M, like so, and then we get the explicit sum, and that sum is equal to the two spinor sums, R prime of U bar, R prime, P prime, gamma mu, U R of P, and then we normally here would write the contribution from the muon, but we can of course take the contribution here from the M star of the electron line, And from the m star of the electron line, we will get a contribution u bar, r prime, the same thing, p prime, gamma. Now, of course, as we discussed, this here is a Lorentz vector and a Lorentz vector, and the electron and the muon line, when they are connected with the photopropagator, would, because of the g mu nu, have the same Lorentz index. So that's what you would get when you form the amplitude. You would get the same thing when you form the complex conjugate of the amplitude, but you would be wise in using a different Lorentz, internal Lorentz index for constructing the sum. So if you used, for example, mu to contract the electron line with the muon line in the amplitude, then you should use another, say, nu, in contracting the electron line with the muon line in the m star. So from the electron line, I didn't use nu, I used rho, mu r prime of p prime gamma rho, u r of p, complex conjugated, and then we have a sum over the muon spins of, which is the same thing, u bar s prime of k prime gamma mu. That was the thing that was connected with this contribution up here by the photon propagator. And then a u bar of s prime k prime gamma rho u of s of k star. Sorry, here we've of course written this. Use the fact that the gamma mu g mu nu gamma nu can be written as gamma mu, right? That we used. It's right here, gamma mu, gamma rho. Good. Now, in order to evaluate these products, we'll use some of the results we've derived earlier. Let's look first at the contribution here from the electron line. The top bit here. Concentrate on that first. Now, since the construct u bar gamma rho u, and let's take this star, is a spinor number, so it's for each complex number for each row, for each choice of row, this is just a complex number in spinor space, then its complex conjugate is also the Hermitian conjugate, right? If you just have a number, it doesn't matter whether you transpose that number. So let's, for fun, choose that instead of just thinking of this as a complex conjugation, we think of it as a Hermitian conjugation. And then what we find is that u bar for spin r prime of p prime gamma rho u spin r of p complex conjugated, bit that we have up here. Let's think of it as Hermitian conjugation, then the spinors come in the other order. So what we have here is u Hermitian conjugation r of p gamma rho Hermitian conjugated, gamma 0 Hermitian conjugated, u r prime of p prime. Now this is equal to the Hermitian conjugation of spin r of the spinor with momentum p of course, gamma rho, gamma 0, Hermitian conjugated, is equal to, let's do it the other way around. Oh no, rho here is equal to gamma rho, Hermitian conjugated, gamma 0, Hermitian conjugated, and gamma 0, Hermitian conjugated, is equal to gamma rho, gamma 0. Good. So what we have here is U bar and then gamma 0, gamma rho. U R prime, P prime, which is equal to gamma Hermitian conjugated, gamma 0, is what we usually call just the notation gamma bar. Then we have a gamma rho, and we have a U R prime, P prime. Good. Now, we want to use now the sum that we had over spin of a spinner with a fixed momentum, the sum of the product U bar, and used the fact that they would sum over spin would give us P slash plus M. We derived that earlier. So if we look at this double sum here, and use how we've just written the star here as a product that is U bar R of P, then conveniently that links up with a U R of P here. And we have to sum over R and R prime. So therefore, what we get is that the sum over R and R prime of U bar R prime of P prime gamma mu U R of P, and then what we've just written, U bar R of P gamma rho U R prime of P prime. We just, oops. That's what we have here, exactly. Now, this is equal to, when we sum over R, U bar R, we get P slash plus M. So therefore, this double sum here becomes just the sum over R prime of U bar R prime P prime gamma mu P slash plus M gamma rho U R prime P prime. Now, we've used here let's say that this was the electron line, so this was ME. We'll just use little m for that. Now, we can actually simplify this even further, because remember that the U bar, the gamma, the P slash, the gamma, the U are spinors, vectors, covectors, or matrices in spinor space. Now, to manipulate that a little further, let's introduce the spinor indices. Instead of writing them as a vector, a covector, a matrix. That was the one here, really, in spinor space. Another matrix and a vector. We introduce the component index notation for that, so we can manipulate it a little bit easier. Good. So in order to do that, we have, or in order to show that explicitly, we have here the sum over R prime, something that is a U bar, R prime. Let's get rid of the P notation, momentum explicitly, and just write it I, right? That's a sum over I of 1, 2, 3, 4. There's a gamma ij, which is the gamma mu, the p slash, the m, the gamma rho. That's just some matrix ij in spinor space, and then there's a u, r prime, with a spinor index j. So gamma here represents the string of gamma matrices, or matrices in spinor space. Now, since we've explicitly labeled the component, we can swap the order of the terms. The U, the gamma, and the U, the order here is important because it's a matrix multiplication. Here it's just component multiplication because we've written out the explicit component indices, so we can reorder them. So we get here the sum over R prime gamma ij u R prime j u bar R prime I is equal to gamma ij. Now u bar, if it was summed over all spinor indices, would give us, just like you did here, p slash plus m. If you only have the j and the I components of the u and the u bar, then you get the ji component of that p slash plus m matrix. So actually what you get here is p prime slash plus m1 always ji. Now this, if we write out what the gamma ij actually was, then that was gamma mu p slash plus m gamma rho, and then from the last bit here we had a p prime slash plus m, and if we then have the gamma ij and then p slash prime plus m ji, then that's equal to the j is just a multiplication, which is why we've just written it as a spinor string here. But the I and the I means that we take the trace over this. Now, these are all matrices. It's of course not surprising that we end up with a trace of all the matrices because the scattering amplitude is just a complex number, not a matrix or vector in spinor space. So it's not surprising that we end up with a trace to get rid of all the matrix notation in these, because all of these here, right, are matrices. Yeah, gamma mu is a matrix in spinor space, p slash, gamma mu, p slash. In order to reduce that to just a number, we take the trace. So now, what we need to be good at is to evaluate the traces of a lot of gamma matrices. So that's just sit down and calculate all the bits that one can do. Now, we have here, there's, for example, the maximum number of gamma matrices that appear is 1, 2, 3, 4, right? So in this specific calculation, the highest power of gamma matrices is 4. There's a lot of odd numbers. For example, if you take 1, 2, 1, 2, if you take all the m terms, so you get only 2, but there's also a lot of odd numbers if you take 1, 2, 3, or the other combination that gives 3, and there's also a combination that gives just 1, which is the gamma mu with the m. No, there was another gamma mu that gives us 2. Well, anyway, you can get 3 gamma matrices out of this, right? If you take that one, you don't take that one, you take that one, and you take that one. That gives you 3. Good. Luckily, it turns out that the trace of any odd number of gamma matrices is equal to 0. So that bit of the calculation is quick. Also, the trace of gamma mu, gamma nu turns out to be 4 g mu nu. You'll show this in one of your worksheets. Now, specifically, as I said, we then need the trace of up to highest 4 gamma matrices. The trace of gamma mu, gamma nu, gamma rho, gamma sigma is equal to 4 g mu nu, g rho sigma minus g mu rho, g nu sigma plus g mu sigma, g nu rho. So if one works through all of this, then this trace here, let's call that star, is equal to, right here, one takes the p out, so we haven't used nu, and we haven't used rho, say, so one can use p slash here and write gamma nu and gamma rho, such that it just becomes gamma matrices with the explicit momenta outside of the trace. Then one gets that the star is equal to 4 p nu p prime sigma. I see there was sigma, not rho, they're taken out. G mu nu, g rho sigma, minus g mu rho, g nu sigma, plus g mu sigma, g nu rho, plus the contribution where one has the m's, g mu rho. Oopsie. Good. Now the same series of steps for the muon line would of course give for k, let's call them alpha, k prime beta, g mu alpha, g rho beta, minus g mu rho, g alpha beta, plus g mu beta, g alpha rho, plus the muon mass we call capital M, g mu rho. Now, if we substitute that into the equation for the matrix element squared, see how far up that went. Oh, that's here. Right, so we've now worked on the electron line, and the muon line separately, if we substitute into the equation for the matrix element squared, then one finds that the matrix element squared is equal to, there's a 4 there, so that you get 8 e to the 4 over q squared, and then there will be a lot of contractions of p's, p prime, k, and k primes. And if you work out with all the g mu nus, then what one gets is a pk, a p prime, k prime, so dots of the 4 vectors, plus p dot k prime, p prime dot k, plus 2m squared, capital M squared, minus capital M squared, p prime, minus m squared, k dot k prime. Good. So now the square of the scattering amplitude is written in terms of the form momentum of the incoming and outgoing states. Actually, it can be written in terms of the masses and the Mandelstam variables. So we can rewrite this in terms of S, which is the square of the sum of the incoming momenta, and T, which is just q squared. So what we have here, for example, is that S squared is the sum of the incoming momentum. So if you square that up, then you get that 2 p dot k is equal to S minus m squared minus capital M squared, where these is the square of, that's p squared and that's k squared, right? So that's equal to what we just called S minus m squared minus capital M squared. One also finds that, for example, 2 p dot p prime is equal to minus p prime squared plus 2m squared, which is minus q squared plus 2m squared, and that 2 p dot k prime can be written as 2 p dot p plus k minus p prime, which is s plus q squared minus m squared minus capital M squared. Now all of the invariants can be written just in terms of S, T, and the masses. That's not really surprising because we know that in a 2-to-2 scattering, there are only 2 scattering angles that will parameterize the scattering amplitude. So S minus M minus capital M, that's a 2 k prime is equal to minus q squared plus 2 capital M squared, and 2 p prime dot k is equal to S plus q squared minus m squared minus capital M squared. Right. All of these are evaluated by, you start from this expression here. For example, that will give you a p squared minus a p prime squared minus a 2p dot p prime, right? So that then you isolate for the p dot p prime. The p squared is equal to m. The p prime squared is equal, the p squared is equal to m squared. The p prime squared is equal to m squared. So you add them with that sign there, and then you isolate just the p dot p prime. Good. So if one substituted in this expression every time one saw a p dot k or p prime dot k prime, then one would arrive at a form for the matrix element squared, scattering amplitude squared, as spin average. Sorry, I should have had that as well. It's a spin averaging here that allows us to get rid of the first set of spinners by summing over their spin. Good. So this is equal to 2 e to the 4 over q squared squared s minus m squared minus capital M squared plus s plus q squared minus m squared minus capital M squared plus 2q squared m squared plus capital M squared. Now, the Mandelstam invariants are S, T, and U. We haven't used U yet. Here we had q squared is actually equal to T. So if we define also the Mandelstam variable U, which is P minus K prime, so the crossed term squared, which is of course also equal in the 2 to 2 case P prime minus K squared, then the spin averaged and summed scattering amplitude can be written as 2 E4 over T squared S minus M squared minus capital M squared plus, and here we then have the U minus M squared minus capital M squared plus 2T M squared plus capital M squared. So this is our final expression for the spin averaged and summed scattering amplitude expressed in terms of the Mandelstam variable S, T, and U, and the masses of the electron and the muon. Of course, it's particularly simple in the massless case, where it's just 2 E4 over T squared S squared plus U squared. But here is the full expression, including the mass terms for the muon and the electron. Now, in order to get the cross-section, one would then need to integrate over the scattering amplitude. But let's celebrate for a moment that we've expressed here the scattering amplitude in terms of invariance. One point here, of course, is that a lot of the work was done in order essentially to write the square of a complex number in terms of invariance. If we were confident enough in working with spinners numerically, then we would have just stopped all the way up here and had our M written in terms of spinners. We would then have evaluated that for a specific choice of the spin up and spin down states, and then explicitly summed and averaged over the spin states of the incoming and outgoing particles. That could all have been done numerically, and then all of this would not have to be done. And that indeed is how many modern programs work when they want to evaluate scattering amplitudes. Of course, if you want to understand the scattering amplitudes and their behavior in certain regions of phase space, then it is necessary, to have expressions in terms of those regions of phase space, for example, large S, small t. Thank you.